Hello, everybody. How many of you, just quick show of hands, know what normal mapping is already? Okay, that's pretty good. So, you know, for a long time, graphics, getting better graphics, it was all about, you know, more polygons, we gotta get more polygons. You know, there's only so much you can get out of that. You know, everything still looks a little blocky. What are you gonna do about it? Well, when we got to a point where we had programmable GPUs, we were able to start using techniques that had been around for, you know, rendered graphics for a long time. So back in '95, some people came up with a technique called normal mapping, which allowed them to use textures to convey information to the shader to describe what the surface of an object should look like. And that's what normal mapping is, or one type of technique to do that sort of thing. Now, we tend to do something called tangent space normal mapping, usually in the game industry. There are other types, but what I'm going to be focusing on is the tangent space normal mapping. So, normal mapping, how it works. We're going to start with a little bit of math for you. First, we're going to talk about vectors. Now, don't get scared. I'm going to try to stick to the high school level math here, so don't freak out on me. Now, you probably had to plot points on a graph back in high school, you know, in geometry or whatever, kind of like this. You remember that? Well, you usually had numbers instead of x and y, but, you know, that's basically what it was. But if you draw a line, see, to that point, then all of a sudden, hey, you've got a vector of xy. That's not real hard, is it? Now, a vector is just a direction and length. That's all it is. We usually call the length magnitude, but it's just a length, whatever. It doesn't have to start at 0, 0, like my earlier example. So, you know, you can move it all over the place. It's still the same vector, as long as it's the same direction and the same length. No big deal, still xy. Now, vectors can be used for all kinds of cool things, like the motion of objects in physics, you know, velocity, acceleration. It can be used for rays of light from a light source. If you're an XNA programmer, you can use it for what direction the thumbstick is pointing. Also handy. Sometimes we only care about the direction, so we do something called normalizing the vector. That turns it into a unit vector. Basically, we force it to a length of 1. We do that by dividing each component by the length. But I don't expect you to remember that. You can just use a function for that in your shader. When we have a vector v, we can indicate the normalized vector with a little caret over it, and we call that v hat. Sounds really silly, doesn't it? Now we're going to talk about vectors on a 3D surface, since we're talking about surface stuff and shading. So surface normals, see that spiky ball there? Basically, those are like normals sticking out from the surface of that clay ball. The normal vector is perpendicular to the surface of a model. You guys remember perpendicular from high school, right? Parallel, perpendicular. All right, we got it. Tangent vectors are parallel to the surface, but they touch it. So you got the ball, and it touches the side of it, just like that. Just like this guy right here on the side of the clay ball. Whoops. We should be... It lost its position, my goodness. Okay, here we go. Okay, the binormal vector is one you don't hear about as often. Basically, it's the one that's perpendicular to the other two. So you can see it sticking out the side here. You've got the normal sticking up, tangent sticking this way, and the binormal sticking out that way. And so you have your 3 axes. You'll figure out why this is important in a moment. First, we're going to talk about something called the dot product. Given 2 vectors, you basically multiply x by x, y by y, z by z, and then you add all those up. Real simple, but you know what? You don't need to remember that either, because you have a function for it. Here's what you need to know. v1 hat dot v2 hat equals the cosine of theta. And you're like, oh no, I don't remember cosine. Was that the one that starts at 1 or the one that starts at 0? I'll cover that in a moment. But this will come up again in a moment. Shading time. All right, we're going to talk about Lambert shading, which is a type of diffuse shading. It's way simpler than you would ever imagine. Basically, you need 2 pieces of information. You need the normal vector. That was the one that was sticking out from the top of the ball, remember? Perpendicular to the surface. And the light vector. That's the direction the light's coming into that point. Theta is the angle between n hat and l hat. And the shaded color in Lambert shading is cosine of theta times the color. Really simple formula. So if you look at my little diagram here, you can see you've got about 180 degrees theta at this point right here. And the cosine is 1 at that point. That means you're 100% lit. And up about here, it's about 60 degrees, you can see. And the cosine of theta there is about 0.5, which means you're about 50% lit. And you can see it's kind of gray there. And then over here, it's 0, which means it's what percent lit? Thank you. All right. You guys are experts already. Check this out. Now remember that cosine of theta, which we were just talking about, is also equivalent to v1 hat dot v2 hat. So the formula for Lambert shading is shaded color equals normal hat times light vector hat times color. Or rather, sorry, that's dot. N dot L times color. Really simple formula for Lambert shading. Now we're going to get to the normal maps. We map textures onto models, kind of like how this label is mapped on the can in my picture. But textures can be things other than just a color that you're sticking on a model. You can convey any kind of floating point information in that texture and pass it to the shader. Then the pixel shader can use that data for anything you want inside there. So here is a quilt square normal map. You don't see those very often, do you? Normal maps store adjustments to the surface normal. So it's telling the shader how it's changing the normal that would normally be sticking out perpendicularly from that surface to make it look different. The red channel from the texture represents adjustments in the direction of the tangent vector. You remember the tangent vector, right? That was the one that was parallel to the surface. The green channel represents adjustments in the direction of the binormal vector. That was the one that was perpendicular to the other two. If it's less than 0.5, so half gray, it's a negative adjustment. If it's more than 0.5, it's a positive adjustment. So, as you recall, here's our little diagram again. If it's positive, if it's a red that's greater than 0.5, it's going to lean towards this tangent. And if it's less than 0.5, it's going to lean away from the tangent. And if it's greater than 0.5 green, it's going to lean towards the binormal. And if it's less than 0.5, it's going to lean away from the binormal. And we're going to pass that into that Lambert formula, which we showed you. And that'll give you kind of that contoured look that the normal map gives you. Now, this is the final formula that does what I just said. The adjusted normal is normal plus red minus 0.5 times the tangent. Now, this is the normalized tangent, so it's tangent hat, plus green minus 0.5 times the binormal hat. Now, let's go to the shader. I'm going to show you code. I know, scary. So first thing we're doing here, and this is the whole pixel shader to make this work. It's not that much code. So here we're pulling in the diffuse color. That's this polka dot thing here, the quilt fabrics. And here we're pulling in the normal map. And here we're pulling in the light vector, which looks like it's coming kind of from this direction. And then we're going to pull in the normal, the tangent, and the binormal. Most of this stuff is just passed in by the vertex shader. You don't need to worry about that. We're just looking at the pixel shader right now. Now I have some code commented out here. And you may recognize this little bit right here because it looks just like this. It's the same exact thing. There's your little red, and there's your little green, and you're multiplying it by the tangent and the binormal, adding it to the normal. Pretty cool, but I have it commented out, so it's not working right now. And that's why this looks like a smooth ball. And then we're going to normalize that, but we're also not doing that yet either. Mostly you do that to get it back to that length 1 because we don't care about the magnitude after we're doing all this crazy math up here. And then the last thing we're doing is we're just passing that normal and the light vec dot. Remember I told you got little functions to do this stuff? So light dot normal times color, it gives you the Lambert shading, just like we talked about before. Okay, so what we're going to do is we're going to remove this little comment right here. So it makes this happen. And then we're going to save it. And we're going to compile. And look at that. Check it out. Now you've got normal mapping. And now you know how it works.